Okay, thank you very much. So today I will give a short introduction to our image similarity prize. Well, how we tried to drop geometric algebra into some recognition. I need to figure out, yeah. So the main plan of the work is I will speak a bit about perceptual hashing, about the main problems of perceptual hashing, and then just short introduction to geometric algebra for conics, because I don't know if anyone used it today, so just to recall what is going about. Then I will discuss our algorithm for finding the transformation and show the simulation results. Well, what's a perceptual hashing? It's widely used for the tasks that require some matching of some similar images. So generally, perceptual hashing generates a fingerprint for each image, and therefore we can map similar images into same or somehow similar hash code. 5 of the most used hashing techniques are the mostly known ones are the average hash technique, difference hash technique, perceptive hash, which we are gonna use today, wavelet hash technique, and singular value decomposition hash. I will shortly discuss some main points. What is it about? Average hashing technique produces a hash value of image based on its low frequencies. They're representing the image structures and pointing out the higher frequencies, which corresponds to the image details, to what we see there. The difference hash technique is slightly different, but it's mostly similar to a hash. Both of them are focusing on the image structure, which is achieved by eliminating of higher frequencies. But the main difference is that in the D-hash technique, we are considering also the change of color gradient between the adjusted pixels, image matrix, etc. Perceptive hash, or so-called p-hash, is extension. It's also the extension of a-hash technique, and what we are adding the discrete cosine transform. Using it, we are obtaining the most sensitive information from our human vision system. Then we can just jump to the wavelet hash technique. It's obviously using the discrete wavelet transformation, and therefore it generates perceptual hashing. And the singular value decomposition hash it was introduced by Professor Kozak, and the general idea was to derive secondary image from the initial image and to get it pseudo-randomly extracting features. And this image will approximately demonstrate our geometric characteristics. A bit of geometric algebra for conics would not be extra because it's Clifford algebra with the signature is 5-3. So we are getting into embedding of the point from the real space by the embedding operator. And we are getting our brilliant basis. In our brilliant basis, we have 2 Euclidean parts, like basic elements E1 and E2, first Euclidean, second Euclidean vector. We have 3 origins, n plus bar, n minus bar, and n cross bar, and 3 infinities, n plus, n minus, and n cross. And with the following embedding, we are getting to our space. What we are going to use today are the transformations in geometric algebra for conics. But before transformations, we will just shortly I will show the basic element we will today use. We will mostly jump to ellipses. So ellipse in geometric algebra for conics has outer and inner representation, and its inner representation is demonstrated here. So we obviously have all our origins, all our infinities, and some parameters where, for example, U and V are the center, the coordinates of the center of our ellipse. Transformations which will be used would be our usual transformations: translation, rotation, and scaling. We are usually applying any of these transformations by the this sandwich product of like we multiply conic from one side and the other side by our transformation parameter, let's say that. Well, we're having translation here. Rotation can be represented with our three rotors, and main difference from other algebras is scalar, which is widely used, and we are applying it the same way. I will get back to the scaling. Yes, we are scaling by the positive line. What we are also going to use in our simulation is the iterative conic algorithm, which was already demonstrated by Pavel Louchka, I think, a year ago, but I will a bit remind what was it about. So we have some different points from our conic, and we want to put some conic into fit it to get the IPNS representation, and we do it only using the operations of translation, rotations, and scaling. This would be used, and now we are going to the main part. So mostly to the algorithm of our mapping. What we get, what we start from? We start from two images. They can be different, they can be same, doesn't matter. What we need to make one image as close as the other one is for further comparison. So what we start from, we upload our images, we create binary thresholds, we make everything with contours, and then we extract the main contour. Main contour is our active player with which we are going to work. We will fit a conic into the main contour, into the biggest contour. Which conic will fit? We will fit ellipse because it occurred to be the most suitable conic for different types of the object. It doesn't matter if it's square or not, but the ellipse is getting the shape. Then what we need the how this inscribed ellipse into one picture is related to the inscribed ellipse to the other picture. So now basically we are not comparing picture point by point. We are comparing the main object line picture by ellipse, which we can rotate, translate, extract the angle of rotation, extract semi-axis, etc., etc. So we will consider it on example on our simulation. So we have two pictures. They were done from a drone, real pictures. As we can see that there is the same object on this picture, same house, same road. But hash comparison gave us different result. We just dropped everything into the hash comparison by OpenCV in Python. All fingerprints were compared, and we got the result that there is 30 differences. Just to make note, normally for similar pictures, hash comparison result should drop something less than 10. Then pictures are similar. Here we are getting 30, so it shows that pictures are totally different. But we know that they are same. We see it. We want to fix this usual hash by our geometric algebra. So what we do? We work with the first image. We get the thresholded image, we detect all the contours, we get our maximal contour, which is our house, and just pay attention, there is a piece of the tree grabbed, it doesn't matter for us. You see the object totally doesn't remain something elliptical, but it doesn't matter, we inscribe by the conic fitting algorithm our ellipse. Then we do it with the second picture. Same procedure, same extracted contour, same ellipse. And then we need to extract from the ellipse. We already can extract using geometric algebra for conics using the Clifford package. We can extract semi-axis, angle of rotation, etc. After we extract semi-axis, we can cut our image into some piece, like to get the centered. We just got the bigger semi-axis of the ellipse and cut it circularly. Why do we crop it in a circular way? Just because we can, after that, rotate it normally, and we don't lose anything around there. So if you get back for a while, you can notice that our object was cut off, and then it's ready for further comparison. We crop it thanks to semi-axis. We rotate it thanks to the angle of rotation. And then, so we have first image, second image, and second image after we rotate it. Here we got the result that the angle of rotation should be 83 degrees. So we simply rotate. Then we, as you can see, these images first and third are, someone would tell same. No, they are not same. They're not totally same. If you look closer, for example, at this part, here the object is a bit closer, so it's not ideally cropped. But for hash, it doesn't matter. We drop this hash object, this picture and this picture to our hash comparison, and therefore we get the result which looks ideal. The result is 0. The result is 0 is telling that images are totally same and the object is totally same. Here, just to make a simple note, if we were comparing it by different technique, not the perceptual hashing, but for example by a hash, we will not get the result 0. What is happening? Our hash is doing some help for us. It's denoising, so it will just not notice these small differences, the small shades. Like if you just overlap the images, for us, for people's eye, it looks different. It looks same, but if to compare it, it's super precise, they are different. So actually a hash would drop us the result something around 5, but it's still the same object. So by this simple press step, we can check if our picture contains some same objects, and other advantage of the method is we can easily find the way of the rotation, how we should rotate our picture to overlap with the one we want. Rotate, translate, and also we can scale it. Sometimes perceptual hashing technique is already giving scaling, but with rotation, it's always breaking. So what was done? We proposed the algorithm that is searching for transformation, which is consisting of 3 simple transformations like translation, rotation, and scaling. We don't need anything else. So we can align any object to any object. Thank you for your attention.
Thanks a lot, Anna.
Any questions?
Are there any questions? Yes.
Hello, Anna. It's Joan Lazenby. Nice talk.
Thank you.
If I have an image, say your house, but then an image of a rotated house with shadows, in different lighting conditions, your initial thresholding and contouring step, would it be robust under those conditions?
Yes, sometimes shadows are creating trouble. They are not creating trouble for rotation. They are creating trouble for initial contour extraction, because the biggest contour we can occasionally catch something different, but we can make some more contrast, and then if shadow is smaller, like if it's somehow half an hour difference between taking of the pictures, then shadow is small and it's still working. But if you, for example, try to do the same thing in the morning and in the evening, then the picture will be different. And also, what was the problem? Sometimes our picture doesn't contain any stable object.
Yeah.
For example, we don't have the house there, but we have trees which are continuously moving from the wind. So in this case, we are getting the problem. But generally, we can consider it as a press step for the further investigation. When we check, okay, we have similar objects, and we can run neural network. But not to run neural network if we obviously by simple check see that, well, there is nothing to search for.
Okay, yeah, great, thanks.
Are there any other questions? Yep.
Hi, Anna. Great talk. It's Eric Wieser here. Am I right in saying that you're aligning the 2 images by aligning the parameters of the ellipses?
Once again, please, I couldn't hear it properly.
Is the microphone working?
Yes, it does, but I hear some words.
Yeah. So am I right in saying that you align the 2 images by matching the parameters of the ellipses?
Yes.
So how do you tell whether the ellipse is rotated 180 degrees?
Well, we tried this case. It was if they are properly aligned, these ellipses, we can add one more ellipse for the smaller contour.
Ah, that's a good idea. Thanks.
So, and the smaller contour will be obviously not, it will not give the same result. So we will not simply get, every time if we feel that there is not enough information, we can just drop the biggest contour and take the smaller one, and then keep the procedure.
Great, thank you.